150 million glass ornaments find their way into homes across the United States every single year. This specific figure exceeds the total population count of the country itself. Yet the primary source of these fragile spheres is not a local industrial complex, but small, specialized villages in Germany, Poland, and Mexico. These artisan workshops maintain continuous output to satisfy global demand. But this is just the beginning of the process. Why do major corporations rely so heavily on these remote producers? It seems logical to fully automate production closer to the consumer, yet the industry remains anchored in these traditional hubs. The reason lies in the centuries-long refinement of specific glass-blowing techniques. This multi-billion-dollar market depends on manual execution that ensures precise aesthetics. At first glance, creating an ornament looks like simple decoration, but in reality, it involves a rigorous sequence of thermal and chemical steps. One can notice how raw glass tubes soften and glow orange under the directed heat of gas burners. Masters blow air into the material to shape it before it cools. Transition to the next level. A solution of silver nitrate is injected into the globe to create the reflective interior base. External coloring follows, transforming the transparent surface. Factories run day and night to complete these steps. The finished glass objects are carefully packed, ready for their place in the holiday season. More than 500 years have passed since red apples were first hung on evergreen trees to symbolize light. Why did German artisans later choose to blow glass into hollow spheres? The organic fruit eventually decayed, while the new medium offered lasting brilliance. Glass reflected light more intensely than any other material of that time, establishing a custom that spread from Europe to the United States. Today, this tradition supports an industry worth billions of dollars. In artisan workshops, a single piece takes up to 10 days to finish completely. Master craftsmen apply the silver coating inside the globe before moving to the surface colors. One can notice how the detailed brushwork is added layer by layer. But this is just one side of the manufacturing world. At first glance, the final products look similar, but in reality, the speed of creation differs by orders of magnitude. Automated factories turn out 60,000 pieces per hour to meet global demand. Machines shape and paint the spheres in a relentless stream without human intervention. Both rhythms help sustain a Christmas symbol that has endured for more than half a millennium. Half a millennium of tradition underpins the industry, yet silica sand remains the primary ingredient used to make glass. Why must this raw material undergo rigorous refinement before it ever reaches the furnace? To the naked eye, the sand looks pure enough for immediate use. However, inside the plant, it must be refined to achieve the required level of purity, passing through multiple screening stages to remove soil, gravel, and particles of inconsistent size that could ruin the batch. A high-pressure washing system strips away organic matter and fine dust clinging to each grain, churning the substance until it reaches a dry, clean, uniform state. At first glance, the processed sand appears flawless, but in reality, it may still harbor trace amounts of iron oxide. On some production lines, the material goes through magnetic separation to remove these microscopic metallic elements. This step is vital, as iron is a factor that can give finished glass an unwanted green tint. But this is just the beginning. One can notice how the refined silica sand is dried and blended with soda ash and limestone in precise proportions. The consistency of this mixture is critical because it ensures the glass will melt evenly once heat is applied. Engineers strictly monitor the ratio to produce fewer air bubbles and achieve the level of clarity required for thin ornament glass. Once the ingredients are combined, the batch is fed into a continuously operating furnace. Inside the chamber, heat can exceed 2,000 degrees Fahrenheit, equal to about 1,093 degrees Celsius. This thermal energy is enough to break down the structure of the silica grains completely. It is visible how the intense temperature gradually transforms the entire batch into a liquid state. And this is not the limit. At this stage, the material does not become transparent right away. It begins as a thick, cloudy mass and slowly turns into molten glass with high viscosity. Inside the furnace, heat flows are carefully controlled so the batch warms evenly. This prevents cold spots, a factor that can create air bubbles or streaks in the final product. Therefore, at the end of the melting zone, a refining section plays a crucial role. Here, any remaining impurities and trapped air bubbles are removed, allowing the glass to reach the purity needed for ornament blowing. When melting is complete, the molten glass becomes a uniform, bright, and stable stream of material. It flows forward, ready to be drawn into thin glass tubes, the base stock from which every hand-blown or machine-blown Christmas ornament begins. Molten glass leaves the furnace in a glowing orange mass, yet it is strictly forbidden to blow it into shape immediately. Why must the material first be drawn into a long tube? It might appear to be an unnecessary delay in the artisan's workflow, but without this intermediate form, the thin wall would not expand evenly during blowing, creating uncontrolled thick or thin spots. The artisan approaches the molten glass with a heat-resistant metal rod, rotating it steadily to keep the temperature evenly distributed across the blob, then gradually pulls back to stretch the pliable material into a long, uniform tube. The thickness of the resulting tube depends directly on the precise pulling rhythm and the speed of the hand's rotation. Even a very slight change in movement can noticeably affect the tube's weight and how it responds to heat during blowing. Once the tube reaches the desired length, it is moved away from the high heat zone. It is allowed to cool slowly in the open air to stabilize. At first glance, this cooling seems like a passive step, but in reality, the tube is continuously rotated on a heat-resistant rack to maintain roundness. This constant motion reduces internal stress, which is one of the main causes of cracking during blowing or later silvering. Any section showing uneven thickness or slight warping is rejected immediately, since even a small weak point can cause an ornament to break during decoration. Tubes that meet the standard are cut into uniform segments, but this is just the beginning. Because each segment is sized to be blown into a single finished ornament, the glass preform must still be glowing hot and pliable. Its surface becomes the ideal moment for adding color and visual effects. The artisan brings the preform into direct contact with trays of fine-colored glass particles, known as glass frit. Under intense heat, these particles instantly adhere to the surface and begin to soften. Consequently, they bond with the outer layer of the glass, rather than sitting as a temporary coating. This process allows the color to become part of the material structure, giving the surface depth, sparkle, and durability far beyond what paint or conventional dyes can achieve. After the colored frit has evenly adhered to the surface, the glass preform is returned to the heat for a refusing stage. It gets more complex further on. The goal here is not to fully melt the material, but to soften the frit just enough for it to fuse into the surface. One can notice how the colored particles begin to spread, blend, and settle into place under controlled heat, eliminating the boundary between the colored layer and the glass core. This creates visual depth rather than a flat layer of color. Once the color has stabilized, the preform is gently cooled to lock in the surface structure before entering the main forming stage. This is the moment when special effects such as marbling, metallic shimmer, or translucency are effectively frozen into the material. If the temperature is not precisely controlled, the color can burn, turn cloudy, or lose its intended reflectivity. Therefore, the artisan or heating system must regulate heat very carefully to preserve the original tone. Only after the color has become a stable part of the preform is the glass ready for the blowing stage. When the color layer has stabilized and the glass preform reaches a pliable state, the blowing process begins. The artisan returns the preform to the heat to soften the tube walls evenly. Then, air is introduced into the hollow interior with continuously adjusted pressure. Because of the combined effects of airflow and surface tension, the glass expands from within. It naturally balances itself into a spherical shape, a physical property that causes hot glass to seek its most stable form. Throughout the blowing process, the preform is rotated steadily to distribute material evenly. One can notice the wall thickness reducing to only a few tenths of a millimeter, and this is not the limit. In some workshops, the expanding sphere may briefly pass through an open forming ring to keep diameters consistent, but the final shape still depends primarily on the rhythm of the breath and the motion of the hands. Stopping at the right moment is critical. Blowing too far leaves the walls thin and fragile, while stopping too early produces a heavier sphere with less visual clarity. Once the desired size is reached, the ornament is separated from the tube, leaving a small neck in place. This neck is ready for the next stage of structural stabilization. Once the hanging stem is securely attached to the top of the sphere, the glass forming process is complete. At this point, the ornament has its final shape, a thin, balanced spherical body with a uniform colored surface and a precisely positioned hanging point. The glass still retains residual heat, but no further manipulation is applied to avoid deforming the sphere or weakening the joint at the stem. From here forward, the shape of the ornament no longer changes, marking a clear transition from manual craftsmanship to the next production. 1,100 degrees Celsius is the critical thermal threshold where the industrial transformation of raw materials begins its relentless cycle. The production of glass ornaments has evolved from a solitary manual craft into a high-speed automated environment capable of meeting global demand with absolute precision. Molten glass flows continuously through a forming die, which establishes the initial diameter of the tube with rigid accuracy. A specialized pulling mechanism draws the hot material forward at a strictly calculated velocity, ensuring that the wall thickness remains consistent along every millimeter of the line. This mechanical precision is the only way to guarantee the uniformity required for mass production at this scale. But this is just the beginning of the complex process. Mechanical blades slice the stabilized glass tubing into standardized segments, preparing them for the forming stage. Each cylinder is clamped into a rotating fixture and introduced to the flame of an industrial torch. The heat is applied gradually, targeting the specific section destined for shaping. Why is the rotation speed continuously adjusted during this heating phase? To the observer, the spinning seems constant, but it serves a critical physical function. The rotation prevents the softening glass from sagging under the force of gravity, ensuring that the heat is distributed evenly across the circumference. One can notice how the glass shifts color and texture as it enters the optimal plastic range. Once the material is sufficiently pliable, the blowing process activates immediately. Compressed air is injected with calculated pressure, expanding the tube from within. The cylinder swells and transforms into a perfect sphere. For complex designs like teardrops or pine cones, the expanding glass gently touches the inner surfaces of non-clamping molds. These guides define the final silhouette without restricting the material's flow. The shape is set the moment the airflow ceases. It gets more complex further on. The formed spheres move to the silvering station, where their characteristic reflective core is created. A nozzle injects a precise volume of silvering solution into the hollow interior through the stem. The ornament rotates ceaselessly, forcing the liquid to coat the inner walls. A chemical reaction is triggered, causing metallic silver to precipitate and bond directly to the glass surface. One can notice the transparency of the sphere vanishing as the interior turns into a flawless mirror. This internal layer acts as the primary reflector for all subsequent external colors. Excess chemicals are drained, and the ornaments undergo a thorough rinse to remove any reaction residues. From here, the spheres proceed to the painting line. Spray nozzles apply the base coat while the ornaments spin on the conveyor. The thickness of this paint layer is controlled to the micron. A heavy coat would dampen the reflection, while a thin one would expose defects. After drying, the items move to the decoration stage. Hand painting, decal application, or glitter dusting completes the aesthetic. The combination of the internal silver mirror and the external pigment creates the deep, vibrant glow associated with holiday decor. But the glass industry operates on a much larger scale in other sectors. Engineers utilize advanced CAD software to design metal molds for bottle production, ensuring every dimension meets the client's specifications. These heat-resistant forms are installed into the double-blow production line. The process starts with a gob of molten glass, heated to 1,100 degrees Celsius, falling into a preliminary mold. At first glance, the formation of a bottle seems like a chaotic burst of air and motion, but in reality, it is a sequence of events synchronized to the 1,000th of a second. The equipment gradually forces the glass into the shape of a parison, a hollow blank with a formed neck. The glowing parison is transferred to the final mold, where a second blast of compressed air stretches the material until it hugs the metal cavity. In mere seconds, the red-hot bottle is fully formed. Robotic arms with heat-resistant grippers gently lift the containers and place them onto the transport belt. The camera glides along the conveyor as the bottles enter the annealing tunnel. Because rapid cooling would cause the glass to shatter from thermal shock, the tunnel reduces the temperature gradually over tens of minutes. This slow process relieves internal stress, stabilizing the structure. Upon exiting the tunnel, the bottles pass through a rigorous inspection zone. High-speed cameras and optical sensors scan every millimeter of the surface. They detect cracks, bubbles, or neck deformities, instantly triggering the rejection mechanism for any flawed unit. The accepted bottles reach the palletizing area. Automated robots lower large grippers, lifting entire arrays of containers to stack them onto pallets. Protective sheets are inserted between layers to prevent friction damage during transport. Transition to the next level. However, the life cycle of a bottle does not end after its contents are consumed. In many regions, reverse vending machines allow consumers to return empty glass for a deposit. This system transforms potential waste into a steady stream of clean raw material for factories. One can notice the colossal mountains of green, brown, and clear glass accumulating in the yards of recycling plants. Heavy loaders scoop up the material and dump it into feed hoppers with a thunderous crash. The mixture of shards, paper, and caps travels along conveyors to the processing unit. Vibrating screens shake out dust and grit, while manual pickers remove large contaminants like plastic bags. A powerful magnetic separator pulls steel bottle caps from the stream, leaving the glass 80% pure. The remaining shards enter hammer mills, where rotating blades crush them into fine cullet. This granular material melts at lower temperatures than raw sand, significantly reducing the energy required for the furnace. Everything only gets more complicated. The cullet passes through an optical sorting system. Laser sensors analyze the color of each falling particle in midair. High-speed air jets shoot unwanted colors into separate bins, ensuring the purity of the stream. This sorted cullet is then mixed with silica sand, soda ash, and limestone to create the batch for new glass products, including automotive windshields. The mixture for automotive glass melts and flows into a bath of molten tin at temperatures ranging from 1,800 to 2,000 degrees Fahrenheit. Since glass is lighter than tin, it floats on the surface, spreading into a continuous ribbon. The equipment gradually stretches the ribbon using edge rollers to control the thickness and width. The liquid interface ensures the glass becomes perfectly flat, eliminating optical distortions. Upon leaving the tin bath, the ribbon enters the annealing layer. Here, the temperature drops from 1,100 degrees Fahrenheit in controlled increments. Diamond cutters score the cooled glass sheet according to programmed dimensions. A mechanical braking system snaps the pane cleanly along the line. High-speed grinding wheels smooth the sharp edges before the glass enters the washing station. The flat sheets are now ready for bending. One can notice how the glass softens and sags into the curvature of the mold as it travels through a furnace heated to 1,150 degrees Fahrenheit. The precise shape of the windshield is locked in during the subsequent cooling phase. Two matching curved sheets are then paired with a layer of transparent PVB film. Therefore, the sandwich must undergo a lamination process. Heated rollers press the layers together to remove trapped air. The unit is then subjected to high heat and pressure in an autoclave, permanently bonding the glass and film. This structure ensures safety by holding fragments together in the event of an accident. The finished windshields are inspected one last time and packed onto specialized racks, ready to be installed on the assembly line.